In this video, we're going to look at systems that are considered special cases. The first special case is called a dependent system. In a dependent system, the two equations represent exactly the same line or curve. In the first picture, we see, let me see if I can circle these. We start out with these two equations that I'm circling, and notice how they appear to be different. But once we isolate y, we now see that the two equations represent exactly the same line. Well, if the solution of a system is the point of intersections and the two lines coincide, they're the same line, that means they intersect all the time. So every solution on one line is also a solution on the other line. In the second example, you see the same situation. We start out with two equations that look different, but if we were then to isolate y, we would see that they were exactly the same. The other special case is called an inconsistent system. In an inconsistent system, the graphs don't intersect at all, so there is no common solution. In the case of linear equations, this results in parallel lines. I want you to notice that these lines, the blue line and the red line, have exactly the same slope, but they have different y-intercepts. And the same is true over here, but it's just harder to see because notice that the blue equation, y is not isolated. So you sometimes have to do a little bit of work before you can tell what you've got. So here are the three things that can happen when you're given a system of equations. You can have a consistent independent system. That's type number one. That's when you have the curves actually intersecting and there actually is a solution, a point of intersection. There's one solution. The second thing that can happen is you get a consistent dependent system. This is when you have infinitely many solutions because the two equations, although they may look different, end up being exactly the same line. And in the third picture, you can see an inconsistent system where there is no point of intersection and no solution. If you're given equations that happen to be in slope-intercept form, y equal mx plus b form, it's very easy to tell what you're dealing with because when y is isolated, we can see immediately that the slopes match, and we can see immediately that the y-intercepts match. So these are the same line, and there is infinitely many solutions. That's a dependent, consistent system. In the second example, we can see immediately that the slopes are the same and that the y-intercepts are different. So if they have the same slope but different y-intercepts, they're parallel lines and there's no solution. This is an inconsistent system. All right, we're going to do an example of each type of special case. In the first example, notice that I have one y equals equation. So this first equation already has y isolated. But in the second equation, I need to move the 3x to the other side by subtracting. And now I have y equals negative 3x plus 1. Once I have y isolated, then it's very easy to see that my slopes are the same and my y-intercepts are the same. So these two equations represent the same line. So my solution is infinitely many solutions. You have to actually state that. You can't just say same line. That's not enough. Infinitely many solutions. In the second example, y is isolated already in the second equation. In the first equation, I have to isolate y. So I'm going to draw a line at the equals. I'm going to subtract x from both sides. That leaves me with negative 2y equals negative x plus 4. Now I'm going to divide both sides by negative 2 to get y by itself, and that's positive 1/2 x minus 2. Notice I have the same slope of 1/2, but I have different y values of negative 5 and negative 2. These are parallel lines which never intersect, so the solution is no solution. Okay, so we have two special cases. The case of same line, which is infinitely many solutions, and the case of parallel lines, which is no solution. Thank you for watching.